Hi everyone, my name is Datta and I'm here to discuss with you all about my computer vision project, Detection of Wrong Direction Driving Vehicles. This project is completely modeled for left-hand driving countries. These are the contents of my project. My motivation to do this project is that in developing countries like India, a third of the road accidents are caused by vehicles flying on the wrong side of the road. We shall discuss about different scenarios of wrong direction driving vehicles. Scenario 1, Overtaking. We can observe that the car A is actually trying to get into the opposite lane of the road to overtake car B. This can result in an accident with car C and B. The sad part here is that car C and car B were actually following the traffic rules, but they are ending up in an accident too. In scenario 2, which is very common among the common man, is lazy or reckless driving, which is done to save fuel and time. As you can see here, the car A wants to go into the adjacent lane. Instead of going to the opposite lane and then coming back into the desired street, he tries to get into the wrong direction driving lane and tries to sneak into the adjacent lane. There is a very high probability that there can be a car B which is actually driving in the right direction can meet with the car A and end up in an accident. The solution for these problems are to set up a camera, a siren, and an LED light in the middle of the road, and to ring the siren and glow the LED light whenever the camera is able to detect a wrong direction driving vehicle on either or both sides of the road. The solution model is of two blocks. The first block is of the computer vision, where we can detect any vehicle driving in the wrong direction. And the second block deals with taking up the input from the first block and and then trying to ring the siren or glow the LED light appropriately. In this project, we will only concentrate on the computer vision part, so we'll only be concerned about the first block. This is the complete outline of this project. We try to extract frames from the given video and then determine the traffic divider line position using Hough transform. Thereby we get the left and the right sides of the road masks and then individually analyze the optical flow of the left side and the right side using Lucas-Kennedy optical flow method. After finding the directions on either side of the road, we can determine whether the directions are right directions or not. The first step is extracting the frames from a given video. As we can see, the video is that the cars are actually traveling in the right directions on either side of the road. We convert them into the frames as we can see here. I used OpenCV package to do this step. The second step is to determine the traffic divider line position using Hough transform using any one of the frames. To extract two frames from all the frames extracted from the video, I have used a 65th and 66% of all the total frames extracted from the video because I found that this place is where I could find the cars actually in the frame. For the real-time monitoring system, we can take an empty road image and then correlate with every frame captured in real time. And if we get very bad correlation between the captured frame and an empty road, it means that there is some vehicle on the road. So we can take that frame and then do our analysis. I tried to resize the original images from 1080 by 1920 to 200 by 400 size. There are two reasons for this. The first is the computation time for the Hough transforms were very low, and by reducing the resolution of the two frames, the motion between the corresponding pixels of the two frames will be less. So we can apply Lucas-Kennedy method. And as we know, Lucas-Kennedy method is fruitful only for displacements which are very small. Before applying the Hough transforms, the pre-processing steps are very important, like smoothing the image using a K by K smoothing filter and performing the edge detection. We perform a smoothing function on the image to smoothen the edges or remove any sharp noises. And then we perform the edge detection using the X and Y gradients. Thresholding is a very important step because thresholding the edges of the car body or anything objects found on the road is of no importance for finding the Hough transform. So setting a good threshold parameter for filtering out those edges is very important. This is what we could get after doing an Hough transform on the previous image. I was adding the pixel value divided by 255 to the Hough space rather than adding 1 to the accumulator. We can see that in the previous image that the divider was actually having the maximum intensity, so applying this method would be really useful. We can see that there are three bright pairs of spots, one representing the middle road divider, the other two representing the margin lines. I tried to optimize the Hough transform by using the orientation of edges, but I could not get great results when there was lots of noise in the video. I tried to create a video with lots of noise by adding the Gaussian noise to the original video. This is how we could actually get the divider line from the accumulator space or the Hough space. I applied a local maximum detection. I tried to pick up the pixels who had greater intensity value than all of its innate neighborhood, and then thresholding those intensity values was very important. I got a result of finding around 25 lines, and these 25 lines consisted of all the road divider in the middle and the two margin lines on either side of the road. So I tried to use another detector which detects all the lines nearer to the middle of the frame and have an angle of around 90 degrees plus or minus 5. After finding the lines near to the middle of the road, I tried to find the mean of the parameters of the points, thereby detecting a single line, which is our traffic divider line image, as we can see here. After finding the traffic divider line image, we can easily create a right and the left mask. After creating the left and the right masks, we can multiply the left and the right masks on our original frames, thereby creating two independent frames for the left side of the road and the right side of the road. Now the most important part, optical flow. This is the most important step before optical flow, which is Gaussian smoothing. Gaussian smoothing is very important because smoothing our intensity values on the image can result in smoothed XYT derivatives, which will result in smoothed UV values, which are very much important. And I chose Gaussian smoothing over a K by K smoothing filter because Gaussian is a low pass filter. To determine X, Y, and T derivatives from both the frames, I tried to use the Roberts masks of 2 by 2 dimension, and after achieving the X, Y, and T derivatives, I performed smoothing on them because the derivatives obtained were not too smooth, so smoothing them was another important criteria here. The same was performed on the right side of the road. This formula is the most important formula used for U and V detection values from the obtained F, X, T. And here, when I actually obtained the X, Y, and T, I averaged the X derivative and the Y derivative from both the frames. After obtaining X, Y, and T derivatives and using the formulas in the previous slide, we can get UV magnitude and UV direction. Before we get the UV magnitude and UV direction, applying a median filter on U and V is very important as it tries to pick up and smoothen up lots of values because in the U and V matrices which are actually obtained has a lots of salt and pepper noise, something like a salt and pepper noise. Yeah, once after we get the UV directions, we need to plot the UV directions. So before we plot the UV directions, we need to pick up only the pixels of UV directions who have a UV magnitude greater than a threshold value. This threshold value was chosen after running this experimentation over several videos for several times and then choosing a threshold value. This value was purely obtained out of experimentation, and there's no formula to find the threshold value. After plotting the UV directions, we can we need to choose the degree which is having the maximum occurrences in this graph. And for the left side of the road, if this degree is less than 0, then the vehicle is in the right direction, and for the right side of the road, if this maximum degree is greater than 0, then the vehicle is in the right direction. As we can see in this image, that the right and the left side are in the right directions. And just to remind you, this is a left-hand driving model. So the output to the terminal is clearly the vehicle on the left side of the road is in the correct direction, and the vehicle on the right side of the road is also in the correct direction. These were the other results. As we can see here, the left side of the road is in the wrong direction, whereas the right side is still in the correct direction, and the results played from the terminal also reflect the same. In the third scenario, we can see that the left was right in right direction, but the right side was in the wrong direction, and the results reflect the same. There is a case where this can fail, as in this case, where both the vehicles are in the same direction but in the opposite directions. In such a case, we cannot find the directions because, as you can see on the right side of the road, even though there was nothing, but still we could find that the direction, but still we could find something UV directions on the map, UV orientation map. That was because during the experimentation, the experimenter were actually moving and a shadow was moving on the right side of the road. For the explanation of the left side of the road, we could find that the vehicles were actually in the opposite directions. So that is the reason in the UV orientation map we could get both of them. And we found that it's actually the output is a wrong direction because the surface of area of the red car was much bigger than the surface area of the blue car. There is a solution for this, that is to reduce the scope of the camera in such a way that only very small portion of the car can actually be captured, or only a single car can be captured rather than a multiple cars. Thank you.